I am Dr. Sigarkanti. In this video, we study Jacobians. So here, if u and v are functions of x and y, then the Jacobian of u and v with respect to x and y is denoted by g of u comma v by x comma y, or that is equal to dou of u comma v by dou of x comma y, and is defined as the determinant where the first row is the partial derivatives of u, second row partial derivatives of v with respect to x and y respectively. That is dou u by dou x, dou u by dou y. Second row is dou v by dou x, dou v by dou y. Similarly, suppose u, v, w are functions of three variables, say x, y, z, then we can define the Jacobian dou of u comma v comma w divided by dou of x comma y comma z as the value of the determinant where the first row is the partial derivatives of u, second row is the partial derivatives of v, third row is the partial derivatives of w with respect to x, y, z. Okay, so that is first row is dou u by dou x, dou u by dou y, dou u by dou z. Second row partial derivatives of v, that is dou v by dou x, dou v by dou y, dou v by dou z. And third row is partial derivatives of w, that is dou w by dou x, dou w by dou y, dou w by dou z. So this is the definition of the Jacobian. Now, suppose if u and v are functions of x and y, then we denote dou of u comma v by dou of x comma y by j. So, usually we denote this by j. And as here, we know that suppose u and v are functions of x and y, then we can express x and y as the functions of u and v. X is a function of u and v, and y is a function of u and v. Then we can define Jacobian of x and y with respect to u and v as the first row derivatives of x, second row partial derivatives of y. Okay, first row partial derivatives of x, second row partial derivatives of y with respect to u and v. That is, first row is dou x by dou u, dou x by dou v. Second row is dou y by dou u, dou y by dou v, and we denote this by j dash. Okay, so j is dou of uv by dou of xy, then j dash is dou of xy by dou of uv. One small theorem is there, show that j dash is equal to 1. Okay, so to prove this, let me consider, let u and v be functions of x and y. Then j is defined as first row partial derivatives of u, second row partial derivatives of v with respect to x and y. That is dou u by dou x, dou u by dou y. Second row partial derivatives of v, dou v by dou x, dou v by dou y. And if I express x and y in terms of u and v, then j dash is given by first row is partial derivatives of x with respect to u and v. Second row partial derivatives of y with respect to u and v. That is dou x by dou u, dou x by dou v, dou y by dou u, dou y by dou v. Okay, these are j and j dash. Then consider j dash is equal to dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y into, this is j dash, dou x by dou u, dou x by dou v, dou y by dou u, dou y by dou v. Now taking the multiplication here, first row, first column, dou u by dou x by dou u plus dou u by dou y by dou u. So this is the term. And first row, second column, dou u by dou x by dou v, dou u by dou y by dou v. Okay, this is the first row elements. Second row elements. Second row into first column, dou v by dou x by dou u, dou v by dou y by dou u, this term. And second column, second column, dou v by dou x by dou v plus dou v by dou y by dou v. Okay. Now here, what is this term? Here, this is the derivatives of u. As u is a function of x and y, dou u by dou x into dou x by dou u plus dou u by dou y into dou y by dou u. What we are doing? We are differentiating partially u with respect to u. That means this is nothing but dou u by dou u. And what about this second term here? Dou u by dou x by dou v plus dou u by dou y by dou v. U is a function of x and y. Then we are differentiating u partially with respect to v. Okay. So this is nothing but dou u by dou v. Similarly, coming to this term here, this is the differentiation of v partially with respect to v. That is dou v by dou u. This term is dou v by dou u. And what about this term? We are differentiating v partially with respect to v itself. Okay. Dou v by dou x by dou v by dou y by dou v. So this is nothing but dou v by dou v. So dou v by dou v. And here this is nothing but 1. Dou u by dou u is 1. Dou v by dou v is also equal to 1. This is 1 and this is 1. What about this term? Here u and v are two different functions here. Neither u is depending on v nor v is depending on u. These two are two independent functions. Therefore, dou u by dou v is equal to 0. Differentiation of u with respect to v is equal to 0. Similarly, if v is not depending on v, therefore dou v by dou u, this is also equal to 0. So what I am getting here is, this is the determinant 1, 0, 0, 1. Expanding this, I will get 1 minus 0. So it is equal to 1, which is the right hand side. Okay, we are getting this is equal to 1. Next, one more property is there. If u, v are functions of r and s, and r and s are functions of x and y, then show that dou of uv by dou of rs into dou of rs by dou of xy equal to dou of uv by dou of xy. This is just like a chain rule. Okay. Just consider the left hand side and then we prove it is equal to right hand side. So consider this left hand side, dou of uv by dou of rs into dou of rs by dou of xy. What is this? This is nothing but the determinant where the first row is u, partial derivatives of u, second row partial derivatives of v with respect to r and s. That is dou u by dou r, dou u by dou s. Dou v by dou r, dou v by dou s into, this is the Jacobian. First row partial derivative of r, second row partial derivatives of s with respect to x and y. That is dou r by dou x, dou r by dou y. Dou s by dou x, dou s by dou y. Now taking the multiplication here, first row, first column, dou u by dou r by dou x plus dou u by dou s by dou x in this term. First row, second column, dou u by dou r by dou y, dou u by dou s by dou y. Okay, this is the term. Next. Second row, first column, dou v by dou r by dou x plus dou v by dou s by dou x, this term. And take the second row, second column, dou v by dou r by dou y plus dou v by dou s into dou s by dou y. Okay. Now, what is this? See here, u is a function of r and s. So, we are differentiating u with respect to r and s here. Now here R is a function of U is a function of R and S. R and S are functions of X and Y. This term is nothing but dou U by dou X, dou U by dou X. That is, this is nothing but differentiation of U with respect to X partially. That is, this is dou U by dou X. What about this term? Dou U by dou R, dou R by dou Y, dou U by dou S, dou U by dou S, dou S by dou Y. That is differentiation of U with respect to Y. This is nothing but dou U by dou Y. And this is dou V by dou R, dou R by dou X, dou U by dou S by dou X. That is differentiation of V with respect to X. This is nothing but dou V by dou X. And this is nothing but dou V by dou Y. Okay, this is equal to, what is the first row? First row is derivatives of U. Second row derivatives of V with respect to what? With respect to X and Y. So therefore this is nothing but Jacobian of U comma V with respect to X and Y. So that is dou of U comma V by dou of X comma Y. Okay. So this is the result. Now one example, if U equal to X plus Y square by X and V equal to Y square by X, find dou of U comma V by dou of X comma Y. So dou of U comma V by dou of X comma Y is equal to the determinant. First row derivatives of U, second row derivatives of V with respect to X, Y. Dou U by dou X, dou U by dou Y, dou V by dou X, dou V by dou Y. So differentiate. What is dou U by dou X? This is our U. Dou U by dou X is nothing but X derivative is 1 plus Y square is a constant quantity. 1 by X derivative is minus 1 by X square. That is 1 minus Y square by X square. Dou U by dou Y. Differentiating this with respect to Y, X derivative is 1, X derivative is 0 plus. We are differentiating with respect to Y. So therefore X derivative is 0. 1 by X is a constant quantity. Y square derivative is 2Y. That means 2Y by X. So this is our 2Y by X. Second row derivatives of V with respect to X and Y. First with respect to X. Dou V by dou X is Y square constant quantity. 1 by X derivative is minus 1 by X square. That means minus Y square by X square. What is dou V by dou Y? 1 by X is a constant quantity. Y square derivative is 2Y. That is 2Y by X. 2Y by X. Now expanding this determinant. This into this minus this into this. So this into this, if I take, this is our 1 into 2y by x is 2y by x minus 2y cube by x cube. Okay. Next, minus of minus becomes plus 2y cube by x cube plus 2y cube by x cube. So minus 2y cube by x cube plus 2y cube by x cube gets cancelled. What remains is 2y by x. So this is our 2y by x. One more example. If x equal to r cos theta, y equal to r sin theta, z equal to z itself. Find dou of x, y, z by dou of r theta z. So this is the Jacobian. First row partial derivatives of x, second row partial derivatives of y, third row partial derivatives of z with respect to r, theta and z. That is dou x by dou r, dou x by dou theta, dou x by dou z. Second row dou y by dou r, dou y by dou theta, dou y by dou z. Third row derivatives of z, dou z by dou r, dou z by dou theta, dou z by dou z. This is equal to, now we find the derivative here. Dou x by dou r, x equal to r cos theta. If I differentiate with respect to r, cos theta constant quantity, r derivative is 1. So this is our cos theta. Dou x by dou theta, differentiating with x with respect to theta, r is a constant quantity. Cos theta derivative is minus sin theta. This becomes minus r sin theta. Okay. Then What is dou x by dou z? There is no z term, therefore dou x by dou z is equal to 0. Next, second row, derivatives of y with respect to r theta z. So y is here, y is r sin theta. With respect to r, sin theta constant quantity, r derivative is 1. So that is dou y by dou r is equal to sin theta. And what is dou y by dou theta? Differentiating this with respect to theta, r is a constant quantity, sin theta derivative is cos theta, r into cos theta. And dou y by dou z equal to 0 because there is no z term. Dou y by dou z equal to 0. Then third row, derivatives of z with respect to r, theta and z. So z equal to z. Therefore, there is no r term, there is no theta term. Dou z by dou r equal to 0. Dou z by dou theta equal to 0. And dou z by dou z is equal to 1. So this is the determinant. Now we have to expand this. First row, this is expanding this one. We write cos theta into, expanding this by first row, cos theta into r cos theta into 1 minus 0. That is cos theta into r cos theta. That is r cos square theta. Okay, r cos square theta. Next, minus of minus plus r sin square theta into, leaving this column, this row, what I am getting here is minus of minus plus r sin theta into, sin theta into 1 is sin theta minus 0, that is sin theta. That is r sin theta into sin theta is r sin square theta. Plus this is 0, 0 into term is 0. So I am getting r into cos square theta plus r into sin square theta. Taking our common factor, we get cos square theta plus sin square theta, r into 1. R into 1 is equal to r. So this is the dou of xyz by dou of r theta z. Okay, I will stop here. Thank you.